+1. There was supposed to be exam, but we'll do that next week, I guess. So let's talk about chapter 3. We want to learn more about derivatives because they're so awesome. We use derivatives to measure the change. And we saw that change last time when we said that the good old formula for the slope, which was y2 minus y1 over x2 minus x1, which was stretched between 2 points as we can see, delta x over here, delta y over there, and there's a slope m for the line. We said that that's going to change first into the slope of the secant line, and the secant line was given as f of x2 minus f of x1 divided by x2 minus x1, and then eventually by substitutions we upgraded that idea into our f of x plus h minus f of x over h, which was the eventually slope of the tangent line. And this h was that x2 minus x1 at the end, the change in x. We also stated clearly that derivative is a function which generates all tangent line slopes, which means that you can find the derivative using the limit theorem, find the derivative. That will be some kind of function of x. So I'm just going to skip all the work, but if we start with f of x being, let's say, 3x squared minus 2x plus 1, and I'm just going to say insert work here, and then eventually you have f prime of x is equal to 6x minus 2. We get the derivative. So this function 6x minus 2 is the one which can generate any slope of the tangent line. If you say x equals to 3, we are looking at slope m equals 16. X equals 1 over 6, we're looking at negative 1, and so on. So we can find all of the slopes in this case. Now, this section today is going to take all of these derivatives now, slopes, and we want to see what is the relationship between the function f of x, the graph of the function, and the graph of the derivative. Because if we are not going to use it for anything, then we don't have to bother computing it. But we're computing it, so let's see what we can use it for. So going off of the definition that the function and the derivative are related in such a way that derivative measures the change of the function, and that the rate of change is also a function, so it's a graph, we can take a look. Let's just take a look at those slopes. So for instance, if I am to draw a constant function y equals to 3, what would the derivative be for this just by looking at it? 0. That is correct. Now why? There is slope, and slope is 0. Yes. So if you look at this one, if your function is y equals to 3, then the derivative is equal to 0. And you can think about this in two ways. One is, well, what's the slope of our original function? And you say slope is 0, therefore derivative is 0. And to add to that, slope is 0 everywhere. Everywhere. Which means that the derivative is 0 everywhere. Which will lead us into later on to learn and memorize the shortcut derivative of a constant is 0. That's the next section. So we are looking at the graph, and we say slope of this line is 0 everywhere, and because the slope of this line is 0 everywhere, then derivative is 0, because that's what the derivative is, the slope. The other way you can look at this, maybe easier, is to say there is no change. The whole function is constant at all times. It's 3 forever. If you go from negative infinity on x to positive infinity of x, the value 3 doesn't change. It's always 3. Note the wording, does not change. Well, if something's not changing, that it's 0. So the slope is 0. There is no change. All of these are equivalent statements. And we will write this. Now let's go and take a look at the next example. Again, looking at graphs. Oops. Next example could be f of x equals x, which is the good old function y equals x, right? So f of x equals x. So y equals x. And now what would derivative be? Derivative would be 1 at all times. As you are looking at the function on the left, its slope is always 1. Slope is always 1. And that's why your derivative is always 1. Next example. How about if I have a function like this? What do you think is happening now? Some kind of piecewise going on. Yes? Y equals, so what are the, well, let's not even worry about what the functions are. You're saying something about 2, I couldn't hear it, air conditioning. Can you? Correct. Very good. So derivative is going to be 2 all the way up to this point, and then after that point is going to be 0. That's the derivative. Observe that we didn't even bother knowing what the function is. Yes? It doesn't really matter. You can use one or the other. Now, it is very important, guys, you understand this. If you get it on this example, next examples are going to be clearer. Observe this. Do we see over here on the graph, by carefully counting these squares, that the slope is 2? You go 2 units up, 1 unit over. 2 units up, 1 unit over. So that tells us that the slope of that line is 2 divided by 1, which is 2. So the slope of the original function is 2, which means it changes 2. And that's why the derivative is 2. It stops at x equals 1. After that becomes a constant, and we know that the constant has no change in it because, and then that's why the derivative is 0. So just by looking at the original function, we can draw and sketch what the derivative does because we are able to see the change. if you think about velocity and acceleration, and let's ignore the negative part over here. If your velocity is changing from 0, if y-axis is velocity, okay? If your velocity is changing from 0 to, let's say, 60 miles per hour, if the velocity is changing, so this is 0 miles per hour, this is 60 miles per hour, so if the velocity is changing over time, and then you see your velocity was changing from 0 to 60, and then when you reach 60, you were just going 60. What's happening with actual acceleration? Ignore again negative p's. You were pressing the gas pedal here, and then once you, no more acceleration. Acceleration is the derivative of velocity. Acceleration is a change in velocity. So, position is changed, velocity is changing position. So when you want to go somewhere, and we will have actually a full lecture on this. If I'm standing still over here and I want to bail, right? Actually, the proper word is bolt. And why is it bolt? When you bolt things, they should stay put. That makes sense? Oh, lighting. Oh, you learn something every day. All right, thank you. All right, so you want to leave, right? My velocity now is 0, and I'm not covering any distance to get out. What do I have to do? I have to change, using acceleration, I have to change the velocity from 0 to, I don't know, 1 mile per hour, right? And then, it's actually 5 miles per hour, but 17 for me, okay. But you change the, you change the acceleration, changes velocity, and then as soon as you have some velocity, the position starts changing. Not a chicken and the egg kind of thing. Don't apply acceleration, the velocity will never change, you will never cover. Right? It's like 3 steps back. So I gotta think about those physical concepts. You know, when you know calculus, physics is a joke. So you usually show up. All right. So I hope we understood this. Now let's take a look at a spicier example. What is this function? X squared. Awesome. Now, do we know what the derivative of x squared is? 2x. So we have that f of x is equal x squared, and you're telling me that the derivative is 2x, so I'm going to listen to you, because you guys are awesome. On Saturdays, other days, I don't know. Again, observe that it goes through every other square. I hope that by now you figured out that you need a proper notebook for this, which is a square notebook. Yeah, I know. Get square notebook, which is awesome. And then you draw all the graphs perfectly straight. I know, right? It's like both of you in the classroom are doing good. And we said that the f of x is 2x. How and why? Just crank that limit, right? I'm going to go with the good old insert work here. Right? That's where your limit, h goes to 0, goes. With the 3 dots. Because what else are you going to do? Tomorrow is Sunday, right? You fill in the blanks. The goal of today's lecture is not to repeat the last lecture, because that's where you learned the blue. The goal of today's lecture is to talk about the relationship between these two graphs. Another thing that we learn, and we will see more of it as we go to this class, is this notion that the function is decreasing, therefore the derivative is negative, the x-axis. The function is increasing, the derivative is above x-axis. The function is 0. Over here, sorry, the function has a minimum. And we have this. All of these concepts will be back in chapter 4. Yes?
On the bottom right, it's supposed to be f prime with that 2x, right?
Yes, there is a prime there. I will zoom in shortly. Prime. York. All right. So from this example, we see that it's a parabola, and its derivative turned out to be a linear line. Before we had linear line gives linear line. Eventually, derivative of sine is cosine, so those are not the same function. So we don't get the same function back when we take the derivative. When you take the derivative of square root, you get some form of square root, but then the derivative of x to the fourth will be x to the 3, and they're different. They're both polynomials, but they're different. And then there are those crossovers like derivative of ln x will be 1 over x. So you're going from a logarithmic function into a rational function. So there will be that as well. So what we are learning here in this example is that you have a decreasing function, and then the derivative is underneath. You have a minimum, derivative is 0, and you have an increasing function, it goes above. Also, we are looking at the rate of change here, and the rate of change is time constant. Well, it's in this fashion, not constant, it's changing in units. Now, we need to figure out how does this actually work. I am going to draw a few of the tangent lines in here. And then we're going to take a look at the corresponding graph. At the minimum point, which is the vertex, we have the horizontal tangency, whose slope is 0. You have to get used to the fact that your derivative graph is the graph of values of slopes. So, at -1, we have a -1 slope. Sorry, at -1 we have -2. So at -1 it's a -2 value. At -2 is -4, and so on. So what is -4 here? At -2x, the slope of the tangent line is -4, and that's this point. This graph, the y values of this graph are values of the slopes of tangent lines from this graph. So it's not y to y correspondent, it is x to x correspondent. So same x's from here are the x's here. Number 1, number 2, number 3, those are the 1, 2, 3 here. So x is identical. The y values here are the y values of the points through which graph goes. The y's value on this graph are values of the slopes from this graph. Right? Welcome to calculus. So you kind of have to think about those things. So one more time, at 0, we have the minimum for this function. I just realized I should have moved this graph. You know what? I'm going to move it up. I'm going to make it x squared plus 1 because I can. It will not change the derivative at all. Derivative stays absolutely the same. Because I don't want you thinking that it's 0, 0 here, so it's 0, 0 there. Hell no. The value of the x is 0 here, 0 here. The value of the y is 1 here. but the value of the slope of the tangent line through this point at x equal to 0 is 0. So that's that one there. At 1, this is x equals 1, say. We have a 45-degree line because that's how x squared rolls. The value of the slope is positive 1, so, sorry, positive 2. So 1, positive 2. And it goes like that. So the y values of this graph, if you need to write that as a sentence, write it as a sentence. The y values of this graph are slopes from this graph. The values of the slopes from this graph. One more time. The y values from the derivative graph. The y values from the derivative graph are values of the slope from the f of x graph. So the values, the y values from the derivative graph are the values of the slopes from the original f of x graph. So now let's use that So let's put some kind of function f of x. We could go pick the points, do a regression, figure out what it is. Some type of x to the fourth graph, no one cares actually. I want to draw in red over this function the derivative. I am able to sketch the derivative even if I don't know what the actual function is, because I know the rules. I'm going to start by marking every minimum and a maximum value, because at those points the derivative is going to cut through x-axis. Remember the previous example, the minimum was cutting through the x-axis. Because at all of those points I will have a horizontal tangency whose slope is 0. So that's why the red points on the x-axis go through 0. This is good to have two colors now, right? You have one color for your original function f of x and a different color for, so if you have a pen and a pencil, or you have some kind of, and start bringing, obviously, colored pencils to class. This is part Calculus 1 and part art. Get a square notebook too. So we start by labeling all of the min and the max values, which will immediately give us our intercepts, x-intercepts for the graph. Once we have that, we're going to draw one slope is enough, and we see that that's a negative slope, which means that line has to be negative below x-axis. We draw a slope there in between the first minimum and the maximum, and we see that the slope is positive, which means derivative is positive, so we connect these two with a positive piece of a line. We draw a slope between a max and a second minimum. We see it's a negative slope, which means the derivative has to be negative underneath the line. And then we have another positive slope right there. Goes up. Does this look like a cubic function? Yeah. I told you that the one on the top is some kind of fourth degree whose derivative is third degree. Awesome. Another feature of the derivative is the fact that the vertical asymptotes are preserved from the original function to the derivative. If your original function has a vertical asymptote, that vertical asymptote will stay in the same place for the derivative. I will give you a few examples. The derivative of x squared is the derivative of 1 over x is some form of 1 over x squared. They both have the same vertical asymptote at x equals 0. The derivative of ln x, which has the vertical asymptote is 0, is 1 over x that also has the vertical asymptote at x equals 0. So the vertical asymptotes will be preserved. I believe on the quiz you had, what do you have on the quiz? What was the problem on the quiz? Like 1 over, not the cosecant. X squared, 1 over x squared plus 3? Or, oh, everything squared, right?
Or it was 5 over it.
5 over it. Yeah. Something like that. So now let's take a look. So I said, and I carefully phrased that, derivative of 1 over x is some form of 1 over x squared. Let's see why I said some form. Why I didn't say is 1 over x squared. So let's draw 1 over x. Our f of x is 1 over x. And then I said the derivative, now we'll be maybe changing this, is some form of 1 over x squared. Let's just sketch the derivative and see what's happening. So we said that all the vertical asymptotes stay put. The derivative procedure will never change that. So we are going to still have the vertical asymptote at x equals to 0. And then, what are we going to do then? Are we going to draw some slopes? Awesome. So let's draw a slope right here. What kind of a slope is this? Positive, negative, or zero slope? Negative. I need, well, we have now 25 students because one went to a better place. Everyone should know what type of a slope this is. So let's try one more time. What kind of slope this is? Positive, negative, or zero? Negative. Yes, like you had breakfast. Thank you. Negative slope, which means that I get to draw this. Has to be below, right? Because it's negative. Negative slope means that the derivative is below x-axis, negative derivative. And I have to follow the asymptotes. That can change. Now let's draw another slope on the other piece of a line and
Negative.
Now if you look at the derivative, how do I fix the formula? By adding minus sign. Exactly, that was missing. So now you know that the derivative of 1 over x is negative 1 over x squared. We are going to learn techniques how to get this, but just by analyzing graphs. So the original line, the black lines, are for the function f of x, which is 1 over x. The red lines are the derivative. Now, we know, well, I told you there's going to be some form of 1 over x squared. The actual positive 1 over x squared looks like this, right? You had that on your quiz. And the ones that are looking on the bottom are with the minus sign, changing everything. So I would like to see what kind of so here's the wonderful problem 13 from your textbook. And if this happened to be your homework, just find something else. So they will give us -2 to have a vertical asymptote and +1 and then the function does this. Draw the derivative. So it's not confusing, just draw the derivative on the separate one, I guess. I don't know. Make it work somehow. So remember the steps, how to draw the derivative from the graph of the original function. Spot all the vertical asymptotes, spot all the min-max values, place those points first, then draw in some slopes and fill in the blanks. There we go. Let's see how this part of the room is doing. The other one is rocky. So far, good though. Oh, well done, man. Well, yeah, you get another 7 days to study. And you get to do the quizzes again. It's just by the grace of devil happened that way. Yeah. All right. Let's talk about this. So we start by preserving all of the vertical asymptotes. And then we have only one max, which means it's going to go through 0 at that point. Now I'm going to draw for the first piece a negative slope, which means that the first piece must look like this. Since the slope was negative, derivative must be negative. Moving in the middle, I draw the slope tangent line, and then the slope is positive, which means it has to look like this. Draw on the other part, slope is negative, so it has to go down. On the last piece, draw anywhere a slope, and it's also negative slope. And that's how derivative looks like looking at the original function. Vast majority of the classroom had that correct, which is awesome. One more thing. I did speak about this last time, but let's just put it in again. When is the function not differentiable? If the two slopes compete at the same point. The overall function would not be differentiable, but it would be piecewise differentiable. I will give you an example of absolute value of x, which is the good old v function, right? So if you are looking at y equals absolute value of x, and you are drawing the derivative for that, we all understand that looking from the left and looking from the right, we can draw the derivative. So we have a -1 slope, and then we have a +1 slope to the right. Observe that at 0, where you have this spike, you have two slopes competing at the same time. there is a -1 slope coming in from the left and a +1 slope coming in from the right. And we know that the derivative is a function which generates all slopes. You cannot have a slope at the same point to be -1 and +1 because that is against the definition of a function. So we put both open circles there because we do not have derivative at 0 because of the two competing slopes. This doesn't happen at x squared. X squared is smooth, no spike. So the derivative at 0 is 0. And we have a minimum for x squared. And x to the 4th, and so on. But if you have a spike like this, you are going to have two competing slopes, and because we are not allowed, definition of function, right, we are not allowed to have two y values for a single x value, we say that there is no derivative at that point. But please observe that the piecewise derivatives are there. Anything less than 0 has the slope and it's -1. Anything more than 0 has the slope. So piecewise differentiable, globally not differentiable at 0. There are also some other functions out there. And I'm just going to draw another case. Let's say that the derivative, the function looks like this. Now, this is not x squared, absolute x, any version of it, because what's happening here is that you actually have infinite slope. So this is not a spike like the x, absolute x. This is the word is escaping my, trying to remember the word, yay. I can't remember the word. Cusp. Thank you. Cusp. I'm going to circle this and write has a vertical tangency. That means the slope is infinite, which means no derivative at that point. Slope is infinite. Slope is trying to get to infinity. So again, everywhere else, perfectly differentiable. Pick anywhere else. Guys, if you are able to draw a tangent line, it's differentiable at that point. If you are able to draw a tangent line, it's good to take the derivative at that point. So this entire function has one bad point, and that's going to be that point at the cusp. Because there, your tangent line will have infinite slope. Therefore, there is no derivative at that point. You will have a vertical asymptote in the derivative. So no value, and since there's no value, no derivative at the point. Questions, concerns? Anything about the whole experience? Yes?
What are we drawing as opposed to, a vertical tangent?
Well, you would still draw, but it will be a vertical asymptote there. And then you have what? This is increasing, right? So it would go like this, and then the other one is decreasing. You will go like that, something like that. But that will be a vertical asymptote. Okay. We're done with 3.2. We will resume for 3.3. And stop.